Okay, guys, welcome. Today we're going to talk about exponential growth, but now that we have definitions for E and the natural log, we can sort of extend this a little bit more based on those two types of functions, right? So what I want to be able to do in this section is I want to be able to talk about the idea of continuous compounding, right? So we've looked at simple interest, we've looked at compound interest, and now we're going to talk about what happens if you make that compounding continuous. We'll talk about, so we'll make some computations regarding that as well. We'll talk about continuous growth rates, and then we'll talk about a concept known as doubling time. And of course, we'll relate that back to continuous compounding. Okay, now what do we mean by continuous compounding? This is again back to sort of our money scenario here. This is saying that if we want to find the amount in an account that compounds, right, faster than daily, faster than every second, faster than every millisecond, at every moment we're compounding what we've previously gained. Well, sort of related to the fact that we're looking at, so let me put it this way. So if we look at our compounded n times per year, right? Well, we know that A is equal to P times 1 plus R over N to the N times T. We know that if we look at this in a certain way, and say this is 1 plus R over N to the N, and then I'm raising this whole thing to the T. But now, of course, what is this thing in here? If we make N go to infinity, or if we make N get very large, we're going to get that this is an E in there. And what is it? It's E to the R, all to the T. And then by your exponent rules, we get P is equal to E to the RT. All right. Now, again, the variables here still represent the same things. P is sort of your initial amount or your present amount. I'll say initial amount. That's what I said before. Your R is your interest rate as a decimal. And your T is your number of years. Right. And of course, A is your final amount. That's what you end up with. All right. So let's look at an example that involves continuous compounding. All right. So we're going to suppose that we have $10,000 that's placed in a bank account that pays 5% annual interest. We want to know if interest is compounding continuously, how much will be in the account after 10 years. So that's our part A. So in part A, so we're told continuous compound, so that's A is equal to P times E to the RT. Now our initial amount is 10,000. Our R, 5%, so that's 0.05. And we want to know this for 10 years, so T is 10. So now if we plug this into our formula, we're going to get that A is P, which is 10,000, times E, which is that number in the calculator, to the R, 0.05, times T, so times 10. And again, you want that exponent to be in its own set of parentheses when you type this into the calculator, or it will not give you the correct answer. All right, but if we punch this into the calculator, and you can find the E button on most calculators by doing a second and natural log will give you the E to the X. And so if you have E, we want to the 0.05 times 10. And most of the time, the calculator will open up exponent on the E for you. But if we do that, we get $16,487.21. All right, and we're talking money, so we can round it 2 decimal places. Okay, so that's what happens for continuous compound interest for 10 years. Now in part B, we want to compare this to 4 times per year. So now this is where we're back to A is equal to P, 1 plus R over N to the NT. So P, of course, is 10,000. R is 0.05. N is now 4, since we're compounding 4 times per year. And t is still 10, I believe, right? We want to see, okay, yeah, so it's still 10 years. So now with all this in mind, our final amount is going to be 10,000 times 1 plus 0.05 over 4 to the 4 times 10. So now if we do this in the calculator, so I need 10,000 times 1 plus 0.05 over 4, and then we need to raise that to the 4 times 10, right? So if we do that, we're going to get that this is $16,436.19. Right? So that you can see that the higher n is, right, and in this case, n is taken all the way to infinity, more compounds leads to more money. Right? So continuous compounding is going to give you the quickest exponential growth here. All right, so that's sort of the idea. All right. Now, of course, you can extend this. This doesn't just have to be money. This can be any exponential growth scenario, right? So, of course, you could have R is usually still a percent as a decimal. All right, but it'll be called a growth rate here rather than an interest rate. P is still an initial amount. And then T, of course, is still a number of years. Or number of time units, right? If you're talking that it grows at 5% per minute or something like that, then you could say that your T is in minutes or something. Okay, so for example, here we have a colony of bacteria that has a continuous growth rate of 10% per hour. So of course, that first point there tells us that R is 0.10. All right, now again, the fact that we're using a continuous growth rate tells us that we're doing P times E to the RT. Now in part A, we want to know by what percent will the colony grow after 5 hours? Well, if we are not given any initial amount, we can assume that P is 1 and that our initial amount, whatever quantity larger than 1 we get, that's the sort of percent increase, right? And then of course, R was the 0.10 and T is equal to 5. All right, so with this in mind, we get that A is equal to 1 times E to the 0.10 times 5. All right, so if we enter this into the calculator, we get that this is equal to a 1.649 roughly. And since we want the percentage growth, we subtract 1 from that to get rid of the original 100%, and it was a growth of 64.9% after 5 hours. So if they don't give you an initial quality, you can only talk about sort of a percentage growth. Now, if we want to know in part B, how long will it take to grow to 250%, that means that we want A to be not a 2.5. Oh, no, sorry. We do want it to be 2.5, yeah, to grow to 250% of its original size. So we want it to be 2.5. Right? So that's just moving the decimal place over 2 spots. So now that means we want to solve the equation 2.5 is equal to, again, 1 times E to the 0.10, but this time we want to find T. All right, so the setup is a little bit different. So if we simplify, we could say that we really want to solve 2.5 is equal to E to the 0.10 T. Now, since our variable is in the exponent, what we can do here is we can convert this to logarithmic form. So this is a log with base E of 2.5 is equal to 0.10t. But what's a log base E? It's a natural log. So we could say that natural log of 2.5 is equal to 0.1t, and then we can divide the 0.1 and say that natural log of 2.5 divided by 0.1 will give me t. Of course, we enter this in the calculator. We get that t is roughly equal to 9.163. So after 9.163 hours, we're going to grow to 250%. Okay. Now, of course, explain why the answers to part A and part B do not depend on the initial size P of the colony of bacteria is because we're talking about a percentage growth, right? And sort of the idea behind percentage growth is that this is a relative rate of change. All right. And the idea behind a relative rate of change is that it does not matter. Or let's say that the actual amounts do not matter in terms of a relative change. All right, so that's sort of the idea there. All right, so that's an example where we can look at exponential growth. Okay, now another interesting example is we want to know how many years does it take for money to double at 5% annual interest, compounded continuously. So compounded continuously means we're using A equals P times e to the RT. Now the problem is we're not given either of these two. We don't have an initial amount and we don't have an ending amount. And of course, we're given an interest rate of 0.05, but we're not even given a t value either, right? So we only have one out of our four variables. But the other part of this is we want to know how long it takes for the money to double, right? And another way you can think of that is a 100% increase, right? I typically think of it that if you start with 1 and you want it to double, you want it to get to 2. All right. So that's how you can sort of approach these doubling time problems. Now, if we set all this up, we have 2 is equal to 1 times e to the 0.05 times t. And of course, we can convert this again to a logarithmic equation. And this is a natural log because it's log base e of 2 is equal to 0.05 t. So last but not least, we could say that t is natural log of 2 divided by 0.05. So if we do that, natural log of 2 divided by 0.05 is going to give us that t is roughly equal to a 13.86. So if we have 5% interest and it's compounded continuously, it would take you almost 14 years for your money to double, all right, regardless of how much is in there. Okay. Now, some other questions that we can look at here are the idea of approximating doubling time and a doubling rate. All right. So if your R is your interest rate, then 70 over R is approximately the doubling time. All right. Sometimes this is called the rule of 70, right? And of course, the other side of this, so you're saying that this is like your doubling time. Now, of course, you can multiply both sides by R and divide both sides by T, and you could say that your interest rate needed is roughly equal to 70 divided by how long it's going to sit there, right? And of course, these are just approximating formulas, and I won't really ask any questions regarding this, but these are just some sort of interesting things that come up. All right. Now, in example 4, we have that the Dilbert comic shown in one of the previous sections starts at 5% compound interest per year. We have that $100 will grow to $1 million in 190 years. And we can verify this to be at least approximately correct by using, of course, our doubling time formula, right? So we can use, for example, 70 over R is roughly equal to T, right? Now here we're saying that if we do 70 divided by our interest rate, which is 0.05, and wait a minute, I think that, oh no, R is in a percent, so I can just leave this as 5. So this is 70 over 5. would give me roughly equal to t. Okay. Wait a minute, something's not quite right here. Oh, okay, no, this is fine. So now this will give me the doubling amount, right? So if I do 70 divided by 5, I'm going to get that t is roughly equal to, and again, this is just approximation. Of course, when you find 70 divided by 5, that gives you 14. So this tells you that it doubles every 14 years, approximately. Now, how many times do you need to double to go from 100 to 1 million? Well, if we do 190 divided by 14, the answer should roughly be 13.57 doubles, right? So this would be approximately how many doubles you would need. And of course, one last check. If you do 100 times 2 to the 13.57, if we get roughly $1 million, then we're sort of verifying this is approximately correct. Right? And we actually get a little bit more. We get 1,216,121. All right, so that's kind of an interesting example. Again, I wouldn't really ask anything that has to deal with exponential growth as an approximation, but that's sort of an interesting thing that comes up here. Okay, now here I said do not approximate. I want to know what interest rate would be needed so that money will double in 7 years when compounded continuously. And here we'll, once we find our answer, we'll compare it to the approximation. All right, but the idea is that if we're using continuous compounds, I need A is equal to P times E to the RT. Now, if we're doubling, we'll set A equal to 2 as long as P is equal to 1 again. And R is what I'm finding. And I want this to double in 7 years. So if we put all this together, I have 2 is equal to E to the R times 7. So if we convert this, get natural log of 2 is equal to 7R. So R is equal to ln of 2 divided by 7. So if we divide that, we're going to get that R is roughly equal to 0.09902, which is an interest rate of 9.902%. All right. Now, what does our approximating formula tell us? Well, the approximating formula says that R is roughly equal to 70 divided by T. And in this case, T is 7. So you get that this is 10, right? So here, the approximation is not bad. The approximation tells you need a 10% interest rate, while the actual interest rate is 9.9%. So pretty close. All right. So that wraps up this video on exponential growth. Now that we have introduced the idea of E and natural log, I hope you enjoyed, and I will see you next time.